Well, we're going to build the echo processor, and that's the PT2399 surround delay application circuit. I'm going to build the surround sound version as opposed to the echo version. The echo version can take you out to 1/3 of a second delay, and I'm going to go for the surround sound, which is going to be less of a delay, and it's going to be, to me, to my ears, more interesting for that. It also takes, by chance, takes less components to build. It'll be a little faster build, but to me, it's more interesting. So we're going to start building that on this little chip, the PT2399 surround delay application processor. Oh, I forgot. We're going to build it out of eProject's resistors. They have a really nice, resistors. Somehow those capacitors slipped in there. These resistors have a nicely sorted resistors. So I'm going to use those for the resistors, because it's looks like it's no inductors in there. It looks like all resistors, capacitors. And the Joe knows capacitors. Let's see if I can get a close-up of that. 33 values, 545 pieces, 4.7 picofarad to 470 microfarad. As a lot of times you don't have the ones you want. I'm just putting that in there. You don't have the ones you want, but you just get close. Get as close as you can, because they're going to be E12 or E6 values. And so I'm going to build it from that, and as the speech source, I'm going to use the text-to-speech converter or synthesizer that I showed you from the one of the videos, where the Arduino is actually producing the speech. Use that as the source, and then just a regular other speaker as the output, and we'll see if we can get some effects out of it. Well, I know it doesn't look like much, but that's the so far. It's about half built, maybe 2/3. We've got the filtering section over here on this side. Over here is the input filter and section, with the input being here. And this is the input capacitor, and so the input will come in here, filter down through, and now what we need is the output filtering and some of the mid-level filtering that will go in here. So we're getting there. Okay, I kind of jumped ahead a little bit. I didn't want to bore you with me putting together the actual echo processor. This is that PT2399 echo processor. I've got it in surround sound mode because it took less components to put together. I think I've got it in surround sound mode. Let me check. Yes, surround delay mode. It took less components, easier to build, and I really wasn't looking for 1/3 of a second delay on the echo part of it. So I built it up. And let me describe the circuit. Let me show you the circuit real quick. This is the circuit, the schematic for the surround sound processor for the PT2399. And this is used in, I looked it up, it's used in guitar pedals. It's used for any kind of audio effects processor. But I did see it used in a lot of guitar pedals for various echo effects. Now, let's see, is there anything special about this when I was building it? Nothing really special, just a lot of resistors and capacitors, as you can imagine. You have your output here and your input here. Now what we're going to do is we're going to switch over, and I'll show you where those are. Well, let me describe what I'm doing first while you're looking at the schematic. I've got one signal going into the input, into the input. I've got a 100 hertz, 3.3 volt peak to peak signal going in here, and it's making its way into the circuit, and of course it's going to do its delay thing, and it's going to come out here, and it's going to come out delayed. Well, how can I find out if it's delayed? Well, what I did was I put two scope probes. I'm using 2 channels of the scope, one at the input and one at the output, to see if the output is truly delayed from the input. If there's no delay, then the sine wave will be right on top of each other. If there is a delay, well, then we'll see the delay, and we can actually measure it. So let me whip over to the scope. Well, first I'll show you the mess that's the actual circuit. Well, you know circuit boards, this is how they look. This is my output right here, and so that's feeding off to channel 1. Here's my input scope here. Let me use a little better pointer from this side. Here's my input right here. So I'm scoping the input, and then here's my input signal here. So channel 2 will line up perfectly with the signal because it's going to the same input. Channel 1 should show some sort of delay out of that if the circuit is working. Now, instead of turning it off, I'll just sweep up to the scope. I won't bother going over this sine wave, showing you the sine wave, producing the sine wave generator. That's what I'm trying to say. But as you can see, this is exciting. As you can see, we have a delay. The top one, the yellow one, I should say, is that is the output. The blue one is the input, and from the sine wave generator, it's 3.3 volt peak to peak, and you probably can't see it, but it says it's 100 hertz. It is saying 100 hertz frequency, so our frequency is true. It's about 2.5 volts peak to peak. The yellow one is. So we're losing. We're going in at 3.3. We're coming out at 2.5. Does that sound right? Hang on a minute. Let me look at something here. I'll try not to bump the camera. Let me look at something here. Oops, let me turn it off. The blue, I want to know, not period, not width. I love this scope, by the way. No, not time maximum. Menu, Vmax blue. So, oh, what does that say? Max 17.2 volt. I don't think so, no. Max is 2.64 volts. Oh, wait a minute. Oh, I've got my 10 times turned on that scope probe. That's silly. Silly of me. I'm almost afraid to touch it. There we go. There we go. That's better. Let me raise that up a bit. So the blue is input, the yellow is output, and they're both about 2.5 volts. So I must be putting 2.5 volts in there. I thought I was putting 3.3 volts. That's what the sine wave generator is telling me. But I haven't actually, I'm just looking at the screen down there. I didn't actually go down and set it myself. So we have the blue waveform is my input, and you can see it's a little crisper. Doesn't have the noise. Let me zoom in on that a little bit. See, it's a little crisper. So that's coming right out of the sine wave generator. And then you can see the yellow, which is the one being processed through the PT2399, it's got some aberrations on it from noise and whatnot that's going to get going through all that circuitry. But it worked first time. I didn't have to do anything. I did have a lot of substitutions in terms of values. Instead of 5600 picofarad, I had to go with 4700 or 6400 picofarad, something like that. But you go with what you got. I wasn't going to order specifically exactly what it said, because I know we can get a delay. So the next step here, now that we see that we are getting an actual delay out of this thing, is to see if we get an echo. And we'll need two speakers. We'll need one for the input and then one for the output, just to see that to verify that we're getting an echo through here. We should be getting, let's measure that. And if we look at that peak to peak, let's see, measure. No, that's not what I want to measure. Cursor. Where's my cursors at? There's my cursors. And I could do that by eyeball. I don't know why I'm fiddling with a cursor. We're looking at 2 divisions, and it is at 100 hertz. 2 divisions, so it is I'm sorry, I have a raging headache right now, so my brain is not functioning. Not that it might notice, not that you might notice anyway, but I was just too excited about this, and I had to show you. Let me look at something first. Well, if you look at my cursors, I wasn't expecting this. From here to here, we're showing a BX minus AX is a 4 millisecond delay. So we're getting 4 millisecond delay. Now that's interesting. That should be, you're not going to really be able to hear that. Well, you will, but you're not going to really be able to hear it well up until you get around the 10 milliseconds. I've played with this before, not this circuit, but I have played with systems before that echo and give you the millisecond, and you can't really tell a lot up until it gets around 10 millisecond, and then you can really tell it around 20 and then 30, and then of course on from there it just becomes an echo. But to get that hall effect, where you're in a hall, you would get something here, and we're going to play with this. We're going to see. But what I don't have, and what was not in the schematic, is a potentiometer. So it's depending on, you hard code the 27.6K resistor. I know you don't know which one that is. That's the that's one of the resistors in there. R. Okay, R. Pin 6 to ground is what determines the delay. And right now I've got a pin 6 to ground. I've got a blah 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 blah. Looks like a 2.2K, either that or a 22K resistor in there. I can't tell if it's red or orange. 22K or a 2.2K resistor. Yeah, because it was looking for a 27.6K, so I think I've got a 22K resistor in there. So that was the first one there. So what I'll do is I'll put a potentiometer in there, and then let's see if we can play with it. See if we can see those peaks should separate and come together and separate. Okay, here's what we got. What I did is I took out the fixed resistor, and I put in just a little PC mount variable, a little potentiometer, which I will use this with, this little flathead screwdriver to alter. So I'm going to go one way and then the other, and it's 100K. The potentiometer is 100K. Maybe I should have used a less one. I've got a whole slew of them we could use. But you can see as it goes through the different delay, it lines up and then lines up. So with just very little movement on that, actually, I've got a perfect one around here. It's a 20 turn or 10 turn 100K, which would be perfect, and I can't find it because I have such a mess on my desk. So it was Labor Day. I promised I would clean it up, and I didn't. But anyway, the next step here is to play with this with real audio. We can see that it is actually functioning. I cannot believe that I just put together the once and I didn't have to troubleshoot it. Cannot believe that. When does that happen? I didn't get one resistor out of place. I mean, one capacitor out of place. Nothing. Well, anyway, I guess not. So that's working really well analytically, you know, through measurements. Now I want to hook up a couple speakers to it. So let's do that, and I'll be back. Well, I'm going to have to admit some naivety here, maybe a little stupidity on my part. I thought this could drive a small speaker, but it cannot. I'm going to have an amplifier at the output, and which may be bleedingly obvious to everyone. But I thought it would at least drive, you know, one of these little tiny speakers you find. I've got some of those that you find in earbuds and whatnot. I thought at least it would drive one of those, but it's not even driving that. It's flattening out the waveform. So I'm going to have I'll put a 386 or something, a little op amp in front of it to buffer it to the speaker, and the input as well also takes down any input I put into it other than the sine wave generator. So I've tried the text-to-speech and put it in there. It puts out a pretty respectable signal, and it brought it down. So I'm not real sure about that, but it's not bringing the sine wave generator down. So I think it's my problem. It's an operator issue here, not a problem with the circuit. So as soon as I find a 386 or something like that to amplify a speaker, which I know I've got around here, then we'll get back in line with it. Because I want to hear this thing operate. I just think it's really cool right now that we can have this kind of separation between the input and the output of the signal, just based on that resistor. Now let's see if I go all the way down, what happens there. Is he just going to, looks like is he changing frequencies? Doesn't look like he's changing frequencies. Looks like he's just changing his phase relative to the output is all. Although something's happening to the output. Yeah, something is happening to the output. When I go all the way to the other end of the 100K, then they match up. But it looks like we're still not going to get beyond that 5 millisecond. That's going to be the second problem we run into. We're not going to get beyond that 5 millisecond delay in the peaks there. So, I mean, maybe that's enough. Maybe, well, 5, 10, maybe 10 millisecond delay. May have to change some components around or something. Do a little research. And it is surround sound delay, so maybe that's where, maybe that's where surround sound is. Maybe it's in the, the 0 to 10 millisecond delay category or delay time. And but I know if you do grand hall, if you have a surround sound system and you turn it on to grand hall, I've done measurements. I know it's 20 milliseconds, and then plus it's all over the internet. I mean, you can read it anywhere. Let's see. So So the next step is to put I may need an input buffer, and which shouldn't be any problems. And I've got op amps out the yin yang here, and then an LM386. I know I have one. I'll just have to find one. I know I've got an audio amplifier around here somewhere. I'll just have to find it, and let's see if we can get that going. All right, this is exciting. Well, look what I found. A 2-watt audio amplifier. Nice little chip here. Looks like this is what I'm going to have to do to build this up, so it will put out some audio, and possibly just use the frequency generator as the input, and this is the output. But it looks like I can't get. I've tried some of the smallest speakers I have, and they all take the output right straight to 0, and I put resistors in. I just don't know enough about audio output, I guess. You know, they're 16 ohm resistors, or I mean 16 ohm speakers, so I thought that would be enough for it to drive. But there's just not enough oomph there to drive it out of this chip, and I should have known better. But anyway, I've got this 2-watt audio amp. So look, I'm going to put this together. Looks like it's a 16 pin or a 14 pin. I'll put this together, and then we'll see what it sounds like. Well, I'm doing what I can about those lines until I learn the how to capture this, capture the video, and do a little better job of that. But I didn't want to cheat you out of seeing the chip itself and all the pinouts of it. There it is. There's the chip I've got, and I'm wondering if I can use. I've got there's an inverting input and a non-inverting input. I was hoping it was kind of a dual package thing. 2-watt audio, but it says 2-watt audio amp, so I don't think so. But there is an 8-pin package that you can use, and I was wondering if I could use both, the non-inverting input for one of them and the inverting input for the others, one for the input, one for the output, in other words. Let's see if there's any hope of that down here. Pull back a little bit. Always go in the other direction. Oh boy! Oh, look at those lines. There's the schematic, and well, just kind of a rough block diagram and schematic of it. Why did they put these schematics in there? Because that's not the actual schematic of the internal part of the chip. I mean, that's probably a dumb question, but why do they put those? Has anybody ever used that? Do you use that schematic? I mean, maybe for you look at an output transistor, maybe, or maybe how the input is done. If it has an op amp configuration, maybe you do use it. But it's not an actual representation of what's actually in the silicon. It's a simplified diagram. Now, I don't think you can see that, but my supply voltage is 22 volts, peak current's 1.3 amps, 8.3 watts is my package dissipation, which that's hard to believe for that 14-pin PDIP. I don't imagine it keeping 8.3 watts for very long. Input voltage is plus or minus 0.5, so I have to be careful there. And that's let's see, output power 2.5 watts, as it said on that's the banner spec. The gain is typical is 50. Output, let's see, V out goes in, our load is expecting 8 ohms, so it is expecting an 8 ohm load. And output voltage swing can go up to 14 volts peak to peak. That's interesting. It's quite a chip, actually. 0.2% total harmonic distortion. For just a little old cheap chip you buy, I mean, it's really not bad. I mean, you get Get 2.5 watts out of the thing. Bandwidth is 100K. And supply current 7 milliamperes typical, 25 milliamperes max. I don't know how interesting any of this is to you, but anyway, I didn't want to cheat you out of not seeing some of the data sheet, or at least hearing about it if you can't see it. Aha! And here is a typical circuit. Let me zoom past the lines there, hopefully. Those lines are the bane of my existence. And let's see, there's the LM, it's the LM380, as I mentioned, and it looks like it can take even as much as from a crystal cartridge. Well, you can tell that's an old data sheet from an old phono record. So a pretty low input then. And all I need is a few capacitors, got a volume knob, tone control that you don't have to use if you don't want. We're just trying to see, we just want to see input and output, that's all we're wanting. Phase shift oscillator, well, I don't want that messing up with, we're phase shifting, we don't want it to phase shift. There's a bridge amplifier. Maybe I can use it. If you can use it in a bridge amplifier, maybe I can use both sides of this, the inverting and non-inverting. Anyway, I think I'm going to use that top one there to act as the my guide to build it. Okay, there, that one there that you see, the phono amplifier. I'll use it. Well, in an effort to show you the good, the bad, and the ugly, I built up the audio amp, and what you're hearing is what's coming out. I've got 100 hertz, 1.3 volts peak to peak going into the audio processor, the echo processor. Then that goes into the LM380 audio amp, and then what you see on the screen, the yellow, is what's coming out of the amplifier. A big, ugly square wave. So I've done something wrong. I follow the schematic on their phono amplifier, but I've obviously done something wrong, or that's not the appropriate values for this. So I'll find another schematic on the web and put that together, but I wanted to show you how ugly it can be. And that noise you hear is the speaker coming out of, the noise coming out of the amplifier. One thing that's mystifying me is how hot the 470 microfarad capacitor that's going to the output speaker on the amplifier, on the LM380 amplifier. That thing is untouchable. It's so hot, and I don't know why. Why would that be so hot? I mean, I guess the internal series resistance of that capacitor is such that the current that is going through it, going to the speaker, is heating it up. So that's a bad cap. Then it's not going to last long. That's for sure at that heat. So anyway, that's ugly, and so I'm going to find a better schematic, and because I know that's a good chip. That LM380 is bound to be a good chip. So we'll get that squared away, and because I want to hear this echo processor work. And if nothing else, then we might have to figure out a way to input from the iPhone into it and amplify that, and then somehow we can listen to the iPhone and what's coming out. But I got to have a good amplifier before I can do that. But anyway, that's where it's at, and I'll get back to you. Okay, the equivalent series resistance of this capacitor is, look at that, it went in the right direction. Look at that, is 0.2 ohms. So and I've got that set for 100 hertz, which is what we were using. We were using 100 hertz. So at 100 hertz, it was seeing 0.2 ohms, whatever amperage was going through there. I didn't measure that, so I don't know what amps were going through there, but it was happening to hit that 0.2 ohms and was generating quite a bit of heat. And it's not a 470 mic, it's a 390 microfarad capacitor. So, you know, cheapo caps. And I wouldn't be surprised if the top wasn't bulging on that thing. You know what? The top is bulging. I thought that was my imagination, but the top is bulging. Let's see if you can see it. Taking it off there. Can you see that? See that slight bulge? See that? There you go. You can see it there. This is a bad cap. That's what that is. They may all be bad. Maybe that's why I got the whole box for what I did. Well, that is a slight bulge in there, and that's going to get worse at 0.2 ohms. ESR at 100 hertz, which is exactly what I was, you know, running through there, was 100 hertz. So we had 0.2 ohms ESR, and there it is, 386 microfarads. So I wonder if that's what was causing my. Well, I have to throw another cap in there. I don't think that's what was causing the problem. I don't think that's what's causing the square wave of what's coming out of the amplifier. In fact, if you look up there right now, you can see I have a gain. Where am I pointed? There we go. See the yellow line? See, he's really clipping. Oops, sorry. He's really clipping. Did I move that? Okay. So I'm putting too much into there, so I need to attenuate that. I did have an attenuator on there, and it didn't seem to make any difference. I had a 20K resistor or potentiometer, you know, that I could attenuate the signal, and it didn't seem to make any difference. So it could be that I had that wrong. But at any rate, whatever, but whether it's a bad cap or the attenuation, I got to redo the amplifier circuit. I hate to go down and buy one of those pre-made amplifiers. I've got one, but it's in another city. And I've got a real nice one actually in another city that you can use as just a temporary amplifier. It works beautifully. And I hate buying one of those again, especially when I've got the circuitry. I can just build something. And this is something we can overcome this. This is something that, I don't know, it's probably bleedingly obvious what's going on here. And I followed the diagram exactly on the LM380, but it was for the phono amplifier, so that was specifically for very low signals. So what I need to do is find one that's for an intermediate signal, something that would be coming out of this echo processor, an intermediate, you know, like 1 to 3 volts or something like that, peak to peak coming out, going into the amplifier, and then amplified, and then going on to a speaker from there. So we'll do that, and I'll get back with you. Well, we're not going to get to do the sound processor, echo processor. We're not going to get to hear it this time. Maybe next time we'll get to hear it. We did see it on the oscilloscope, and it looked pretty good there. The delay was 5 or 6 milliseconds. And so we're going to building the LM380 didn't work. I don't know why. I built up a couple of different circuits on what I found on the internet, plus another note from Texas Instruments, which had a very simple circuit. Still didn't work. It's putting out a square wave. Maybe the chip is bad, but when I put in a sine wave, it puts out a square wave. So even when I put in the signal generator directly, I skipped the echo processor, put the signal generator directly into it, it still would put out a square wave. So I don't know what's going on there. But anyway, I'll build that up. I'll find an amplifier and I'll leave it built, rather, the echo processor, and we'll get to hear that. But for now, we're going to have to put that on hold for a little bit and get back to the robot. All right.